I greatly appreciate you joining this evening. And as we're getting started, I'd like to cover the chat session disclaimer. This live chat and the Codings Talk series does not represent the opinions or strategies of Akzo Nobel International Paint. Additionally, I make every effort to provide accurate and up-to-date information from the global protective coatings industry. Despite this care and attention, it's very reasonable and possible that the content and chat conversations within this live broadcast may have content that is incomplete and or incorrect. The information and chat conversations on this live broadcast are offered without any form of guarantee or claim to accuracy. No liability is accepted for the consequences from such errors. No agreement shall be reached on the basis of such errors, and recording, distributing, and any other use of this live chat is not permitted without written permission of Jim Kunkel. That's me. I am recording the session again, audio for rebroadcasting and to have an archive recording of this topic. So to set off the live chat, before I set up the topic for the live chat, I'd like to cover how you can participate in this live chat. It's very easy. All you have to do is raise your hand. There's an icon for that in the chat menu. And also please feel free to hit any of the emojis to let me know how you're feeling about this live chat. Okay, I'm going to go ahead and get into the topic, which is concrete cracks, identification, repair, and coating application. I'd like to cover first the basics regarding concrete. Now, concrete starts out as a fluid, a low-strength material that undergoes physical and chemical changes as it gains strength and hardens. In the pre-hardened plastic state, it's susceptible to cracking when exposed to relatively small stresses. Even when it reaches its full hardness, the tensile strength of concrete is only about 10% of its compressive strength, making it less resistant to tensile stresses than many other building materials. Now, the forces that cause cracking in concrete are both internal and external, and likely the result of several combined factors. Cracks are not only something that must be dealt with, but they are a symptom of an underlying problem. Changes in chemistry and temperature causes stress within the concrete itself. Now you have external loads or traffic that can exceed the strength of the concrete, which will cause cracks. And there are preventative measures that can be taken to minimize these forces, thereby lessening the detrimental impact on the concrete, which would be further cracking and the destruction of the concrete itself. Now, if cracks do form, there are many repair practices that are available. Now, some crack repair techniques are designed to prevent significant structural failure or leaking, and others are purely cosmetic. The exact practice required depends upon the length, the depth, the number of cracks, and importantly, whether they are active or dormant, whether they affect structural integrity or not, and the purpose of the concrete structure itself. So I'm going to be talking about some of the causes for cracks. The first I want to cover is chemistry. Now, as I mentioned earlier, concrete is a composite material, and it's built of inorganic hydraulic binding material, which is going to be the cement. Now, it's embedded within a fine aggregate, which is typically sand, and then it has coarse aggregate, which is typically gravel. Now, you add into it water, and you can throw into it admixtures. Now, the rate of strength development and the final strength depends upon many factors, including the mix formula, the water to cement ratio, the placement procedure, and the type and size of aggregate, and as I talked about, the admixtures, which would be your to help out in curing, but then ultimately it's the curing of the concrete itself, the conditions going into the cure. Now, cracks follow the weakest path through the concrete once the tensile strength has been exceeded at any point. If the crack passes through a piece of aggregate, this is an indicator that the aggregate was weaker than the cementitious portion of the concrete. The more equalized the strength, the finer the pattern of cracks. More defects and higher stresses in concrete produce more rapid and severe cracking. Now, cracks in concrete may be classified into those that develop before hardening, which would be in its plastic stage, and those after hardening. So we're talking about in the cure. Now, plastic cracks are usually caused by construction movement, such as a subgrade that moves or formwork movement. It could be the settlement. It could be settlement shrinking, which would be the reinforcement being too close to the surface, or sudden changes in placement depth. And then setting shrinkage due either to plastic shrinking or drying shrinkage. So there's a lot of factors that can go into this into plastic cracks. Now, hardened cracks, the changes in temperature, volume, and chemical makeup that occur during the hydration of the cement produce forces that cause tensile stresses that often result in cracks. Hardened cracking can result from physical causes, which would be drying, shrinkage, moisture movement, chemical action. You could have unsound cement, reactive aggregates, reinforcement corrosion, and thermal conditions, heat from hydration, fire, a coefficient of thermal expansion, the differences with heat and freezing and things like that. So the stress concentrations really impact the structural design. And then also, too, you can have accidents that could cause some of the cracking as well. Now, in the hydration of Portland cement, it's exothermic and can generate sufficient heat and massive concentration to cause cracking from the thermal differential volume changes. As the concrete cools, it contracts, causing stress forces. Now, to prevent cracking due to thermal stress, it's important to minimize the temperature variation within the concrete structure during the curing and to control the rate of cooling. Once concrete is placed, settlement of the subgrade, entrapment of air or water pockets in concrete, movement of the formwork, vibration during setting, premature loading, and improper consolidation all create internal weaknesses where the cracking process begins. These inherent weaknesses combine with environmental stresses that cause the beginning of the first crack, which may be invisible, and the initial crack either continues to grow or widen, or encountering obstacles so its forward path branches out to form a network of cracks, like a spider web. It would hit something, maybe hits aggregate, and it spreads out it fractures out as a spider web look. Now, shrinkage cracks. Shrinkage is a decrease of concrete volume over time. Some shrinkage is inevitable, and to a larger degree, it is very controllable. This is where you do control joints are used to relieve the stress that occurs due to shrinkage in order to prevent cracking. Now, reinforcement steel and aggregates provide internal restraint that diminishes shrinkage cracking. And pre-stress and post-tension reinforcement prevents shrinkage cracking by maintaining the concrete in a continuous compressive condition. Now, shrinking can also be offset by the use of shrinkage compensating cement, or as I mentioned earlier, admixtures. In concrete, there are 5 basic types of shrinkage. There's plastic, settlement, drying, and homogeneous and carbonation. Now, plastic shrinkage occurs when the water evaporates quickly from the surface of the concrete prior to initial setting. The concrete at the surface decreases in volume faster than the underlying concrete, which causes cracks to form. The occurrence of plastic shrinkage cracks can be reduced by incorporating synthetic fibers into the mixture, following proper curing procedures, avoiding placement in hot, windy, or low humidity conditions, and finishing the concrete in the shade. Now, use of evaporation additives that you would put on to deal with that. These would be like the finishing aids or curing compounds. Water fogging or tarping are employed to prevent rapid evaporation of water. You don't want the water to evaporate too fast. But caution must be used not to weaken the surface of the concrete with too much water. So there's a fine balance, a ratio that needs to be achieved. And a lot of it will come with the experience of the company, the contractor, who's ever putting down the concrete. So as concrete paste settles, cracks may form in the weak concrete at areas where there is a restraint, such as over a reinforcement bar or a sudden change in the placement depth. The usage of low sump concrete and vibration during placement and greater concrete over reinforcement helps to minimize plastic settlement. Re-entrap corners and suddenly changes in the placement depth can cause stress concentrations prone to crack formation. Now, let's go into here. Autogenous shrinkage is due to the loss of water from the pores of the concrete due to the hydration reaction with the cement, as well as changes in the volume of reaction products forming the hydration of the cement. Now, high cement contents and low water to cement ratios contribute to autogenous shrinkage. Drying shrinkage is the decrease in volume due to the loss of free moisture from the concrete, where basically it's through evaporation. Volumetric differentials due to variations in moisture loss and restraints due to the decrease in volume causes stresses to develop. And now an example of this would be curling seen in a slab on grade placements, where the top surface of the slab loses water due to evaporation and the bottom of the slab remains moist. Typically this shrinkage is compensated for with control joints, but often some cracks will develop, frequently paralleled with the control joints or bisecting the corners of the slab. Now, drying and autogenous shrinkage can be minimized by techniques to maximize creep and or keep the water in the concrete, such as adjusting the water to cement ratio, proper curing, the use of slower hardening mixtures, and shrinkage reducing admixtures. Creep is a time-dependent increase of strain in hardened concrete subjected to sustained stress, or in other words, of a slow inversible flow under load. A high water to cement ratio may reduce autogenous shrinkage, but typically increases drying shrinkage. A high water to cement ratio also reduces strength, abrasion resistance, and increases permeability. So for some structures where shrinkage must be minimized, expansive hydraulic cements are used to counteract a decrease in volume. Now these cements contain ingredients that react with the hydrating cement and water to form reaction products. And the other thing with this is that concrete made with expansive admixtures usually contains reinforcement to create compressive stresses that offset the tensile strength of the drying shrinkage. Now, carbonation shrinkage is a decrease in volume due to the reaction of calcium hydroxide in the concrete with carbon dioxide to make calcium carbonate. And calcium carbonate has a lower volume than calcium hydroxide. Carbonization can cause significant surface crazing if the freshly placed concrete is exposed to higher levels of carbon dioxide, such as a combustion heater used in a cold water application, or it's running a generator or a compressor. And not much can really be done to prevent carbonization except to ensure that combustion heaters and other forms of combustion are properly vented. Carbonation is also an effect that occurs over a long period of time as atmospheric carbon dioxide diffuses into the concrete under suitable humidity conditions. And since the carbonation rate is a function of diffusion, the depth of the carbonation adjacent to a crack can sometimes provide an indicator of when the crack formed. This type of carbonation I'll probably mention a little bit later here in the conversation this evening. Now, cracks due to expansive reactions. Carbonation can cause cracking in concrete by contributing to the corrosion of the steel reinforcement. The high alkalinity of the concrete helps to prevent the rebar from corroding by formation of a passive layer. On the surface of the steel. The reaction of carbon dioxide with calcium hydroxide lowers the pH of the concrete. Now, if the pH of the concrete surrounding a steel reinforcement falls below 8.5, the corrosion of the steel will begin, even in the absence of chloride ions. Now, with the presence of chloride ions, whether introduced in the concrete mix or penetrating into the concrete through the cracks or the diffusion, further will accelerate the corrosion of the reinforcement steel, lowering the pH and increasing the chlorine ion concentration. And what this is basically it's a cycle that will continue to work that corrosion, increase the severity of that corrosion. It's a cascade that continues to happen. As the steel reinforcement rusts, the conversion of iron to iron oxide produces an expansive reaction product, which causes cracking and spalling of the concrete. The carbonation and chloride ion penetration into the concrete will progress deeper as the concrete ages. If the steel reinforcement does not have enough concrete to cover it, the corrosion of the steel will occur much earlier than if properly embedded. An alkali aggregate reaction, or AAR as it's called in the industry, can be produced when some types of aggregate react with the sodium and potassium alkalis present in the concrete to cause localized expansion, resulting in cracking of the concrete. The next type is alkali silicate reaction, ASR as it's called in the industry. Now that occurs when hydroxide ions associated with the alkalis in concrete react with poorly crystallized silica, and it results in a gel-like material. Alkali carbonate reaction occurs when hydroxide ions react with certain dolomitic limestones to form an expansive reaction product. These gel-like materials can expand when exposed to water, and the expansive forces can cause cracking. Now, to avoid these problems, it's important to carefully select non-reactive aggregates when high alkali cements are used. I always say a lot of times with concrete, it's almost like alchemy. You have to really do it just right, and if you do it just right, you're going to get a good end product, but there's just so much variation that can go into it. That's why concrete as a substrate is such a unique animal versus steel, especially with coating systems. Sulfate attack is another expansive deterioration mechanism. Now, sulfates either permeate into the concrete or they're presented in excess of the concrete mixture, and they react with the cement to form another, destructive result. The same reaction is useful in some types of shrinkage compensating concretes, but unless controlled in the expansive formation of the concrete, you could have pores that will develop, and so you want to use sulfate-resistant cements and admixtures in sulfite-bearing environments, which will prevent this type of problem. So another form of stress is going to be load and then thermal stresses. Now, thermal stresses can cause cracks to form in concrete, and when we look at this, you're going to have, if there's a sufficient temperature, if it swings in a variation, if it can be a variation of degree, it's going to create an expansion situation, which would produce a debonding of the polymer from the concrete, and typically by rupture of the concrete surface. So settlement of foundation or footing on which a part of a concrete structure is based can cause significant cracking. Concrete structures must be properly designed and supported to avoid this. Soil compaction must be sufficient to prevent settlement under the load of the concrete structure. And then the important thing coming up is drainage. It should be there to prevent the erosion of the supporting soil under concrete structures. There also should be some seismic considerations to be employed to accommodate, based on regional codes, building codes, and then the strength, development, and hardened properties of the concrete that's needed to be considered as a very important component of the structure. So if we're looking at a wastewater structure for containment, for example. Now, when settlement is expected, construction methods such as hinge joints may be employed to relieve the stress before cracking occurs, and the use of proper structural design, concrete composition, and reinforcement techniques can minimize the chances of damage due to settlement. We'll go a little bit further into freezing and thawing. It does and it can cause cracking. Freeze-thaw damage is worsened by the ingress of moisture, which gets in. When you think of concrete, it's capillary. Water can pass through it. So when you have a situation where you're going to have moisture getting in, and then you have included with that, sometimes you might have de-icing salts, or you might have other types of things that can act as a component to get in there to really cause some of the additional cracking and deterioration of the concrete itself. But the stress that's caused by freezing water can literally crack and spall concrete. And then cracks that give water transport into the structure can be widened when it's subjected to freezing. So by widening, when it goes through, it freezes and it widens the crack. The use of air and training agents in the concrete can reduce freeze-thaw damage by producing small, correctly sized and uniformly distributed air bubbles that help provide the freezing water a place to expand into. For concrete that will be exposed to freezing and thawing, it's beneficial to use a low water cement ratio and allow curing for at least 30 days before exposure to de-icing salts, any type. Well, obviously you're not going to be coating in the winter in cold weather, but any type of de-icing salts or anything that might go on that as well. Now, okay, everybody's good. I keep looking over to make sure to see if anybody has raised their hand, but thank you guys for still being there with me. Now, concrete cracks due to exposure to excessive load stresses. Since the strength of concrete develops with time, different loads may be accommodated at different ages. Now, fresh concrete can crack if the forms are removed too soon, or if it's exposed to load before sufficient strength is achieved. Fully hardened concrete will crack if it's exposed to loads or traffics and it's not strong enough to withstand. Now, detecting cracks. Before repairing cracks, you have to identify them. You have to chart them out. You have to map them out. Now, the most obvious way to detect a crack is to do a visual inspection. You want to do a visual assessment. However, not all cracks are visible on the surface, and some fine cracks may require magnification to be seen. Dampening of the concrete surface will often highlight very fine cracks. And some cracks are not visible on the surface because they occur within the concrete matrix. And these cracks may be detected with pulse velocity devices. Now, these devices are used to detect cracks that occur within the concrete matrix, and and the voids as well, in concrete by measuring the effect of the velocity of sound waves traveling through the concrete. Impact echo devices detect echoes that occur within a short duration pulse, and it's reflected by a flaw within the concrete. So cracks may be classified by direction, width, and depth. Surface cracks consist of roughly hexagonal patterns of short cracks indicating that the concrete surface had more restraint than the concrete interior or substrate. And directional cracks tend to run in relatively straight lines and may have parallel companion cracks at fairly regular intervals. Directional cracks indicate restraint perpendicular to the crack direction, and directional cracks may also propagate from the restraint corners or penetrations through the concrete. Active cracks continue to grow after the concrete is hardened, and dormant cracks consist of plastic cracks and those formed by temporarily overloading the concrete. Now, when a surface crack is detected, the movement of the crack over time may be monitored with devices such as glue-in-place crack gauges, optical comparators, and extension meters. Whether active or dormant, a crack remains a plane of weakness where movement is most likely to occur when the concrete is subject to stress. So the proper repair method for cracked concrete depends on a number of factors. The first is, what you want to understand, what's the purpose of the structure. Again, determining is the crack active or dormant? Is the crack horizontal or vertical? Is the concrete structure is the concrete structural or non-structural? What's the overall number of cracks that have been identified? Is the crack isolated or part of a pattern? What is the location of crack, where it's located? Is it the surface? Is it near a joint? Is it underneath? And then importantly, what is the crack depth and the orientation in relation to the structure? Is it transverse or longitudinal? And then is weather resistance required? And then the last part of this would be what kind of chemical resistance is required. So understanding what, oh, here we go. Let me bring you up on, if you want to come up on stage here. Susanna? You can unmute yourself and talk. How you doing? Oh, okay. And the other thing too to look at, again, we mentioned about the what is. Oh, you're acting to speak. Okay, let me get back up again. There you go. Just have to unmute yourself if you do want to speak.
Unmute to speak. Okay, can you hear me?
Yeah.
Wonderful. Okay.
Thank you for being here tonight.
Oh, hey, I'm really enjoying it. Just as you're talking, I'm remembering so much of this story with the just the tragedy of the high rise that collapsed in Florida and the spalling of the concrete, and there were that came up over and over and over.
Yeah.
And I wondered, like, if you could just kind of mention what were some things that they could have missed or could have seen, because I don't know, but I know just listening to you talk, I'm wondering what were those maybe warning signs that were missed. And I'll hang up and let you answer, but I'm really enjoying the podcast.
Oh, thank you. I appreciate that. So let me do this while we're doing that. Let me see if I can find that actual report. Oh. Pardon my. So a couple things we're probably talking. You're talking, I think, about the footbridge, right?
Is that the high rise that collapsed?
Well, okay. So the high rise. Okay. So with that one, let's cover that because I do have it up here.
Okay.
That's a Surfside condo in Florida.
Yes. Yes.
So in 2018, a consultant hired by the condo complex had urged the ownership to repair cracked columns and crumbling concrete, and it was not done. Now,
okay,
resulting to that, because what this was, these were cracking and crumbling of columns that were in the walls too, actually, of the parking garage, right? And that was under. So think about Florida, and when you're at, you go ground, if you go a little underground, and obviously, they're going down there, they're going to be dealing with water,
right?
Because, you're literally right at the ocean level there. So over time, if you're not maintaining that concrete and you have rebar, and corrosion was a major issue with this that caused those columns in the walls, which caused, yeah. Now, the same thing when you look at that, the bridge that collapsed, I believe that was that University Bridge, and that was one that was concrete. And what ended up happening with that, you had a situation where, when I was talking about tension and post tension, sometimes if you don't do things the right way, and I'll give you a good example. So when I worked for the Society for Protective Coatings, SSPC, I used to work a lot with the state DOTs. And some of the issues they had with some of the concrete bridges was that you would, over time, although I don't think this really came to bear with that because that was a newer bridge. But over time with some of the concrete bridges, you have steel cables that are in there. And what they do, they're tightened, so they cause tension in there to kind of really increase the strength and solidness, let's say, the really the kind of, you know what I mean, the hold that bridge together better.
Yeah.
Over time, when you have moisture that will get into that through cracks, those steel cables will start to corrode. And so sometimes you have these tension bridges where they actually have they'll have listening devices, like they'll listen for those strands that are breaking.
Oh, how cool. I didn't know
and
that. That's
and
cool.
then there's triggers when they have so much alarms go off, then they know we got to relook at the bridge and things like that. So there's a lot of different ways really to look at, with concrete, but it really comes down to it is if you're not really inspecting it and you're not properly repairing it and maintaining it, and coatings are always a solution. You could do waterproofing. There's other barriers you could do. But if you're not addressing that, if you have any type of rebar in there, it's definitely going to have corrosion. Even on some of the rebar that's epoxy coated and things like that, you can
Right.
still have, you just get one pinhole opening, and that rust, it'll just start to corrode in there interior, and it cascades itself. So
That helps. That clears that up a lot. I appreciate that. I just remember hearing concrete spalding and those type of issues a lot around that story. So I'm that shed a lot more light on it. Thank you.
yeah, thank you so much. I appreciate you being here tonight.
My pleasure.
There we go. Good question. Great question. So, we talked about, the questions you want to ask. Now, for structural crack repairs, repairs of cracks that affect structural integrity must restore the strength of the concrete and frequently require, really, this is where you want to have an engineer come in, and it's the same situation when you're looking at concrete building, concrete bridging, concrete flooring. If it is something that's going to be structural, you really want to get a professional in, someone who's qualified. There's a lot of certifications when it comes. We have the ACI, American Concrete Institute. When it comes to concrete repair, you have the part of the ACI, which is ICRI. Some people call it ICRI. Those are really great professionals. A lot of them are trained or certified, but get somebody that's really experienced that can really go in there and address, look at the crack, look at the structural issues, and then offer a remedy to it. Now, if a crack affects structural integrity and is not dormant and future movement is expected, it's in most cases going to be necessary to modify the structure to include an expansion joint. Now, some other things you can do is what's called an epoxy resin injection. Now, epoxy injection resin is a common way of repairing structural cracks. There's two components of liquid epoxy, and what they do, they're injected in through plugs, and they can be fitted into holes that are drilled along the crack. Epoxy is a very excellent cohesive strength, and it does provide a good repair with strength comparable to or greater than that of the concrete. Now, one thing related to epoxy resin repair, it will not be successful if movement occurs. That's the important thing to understand with an active crack and there's movement. If the stress that causes the crack continues, the epoxy repair will likely, if the stress that causes the crack continues, the epoxy repair will likely not fail, but a new crack will form in the adjacent location. Epoxy resin injection repair is not practical if the crack is wet or if the cracks are too numerous. Now, another method is called stitching or doweling. Structural cracks can be repaired with steel reinforcement to restore tensile strength across the crack. Metal staples or stitching dogs may be attached across the crack where holes are drilled on either side of the crack, and the legs of the staple are anchored into the holes with epoxy or other suitable grout. The number, size, and spacing of the staples are determined by what is necessary to restore the tensile strength across the crack. As with epoxy repair, stitching provides restraint, which will cause cracks to occur elsewhere if continued movement occurs. So think of it as if you have a open air, you're putting staples across that open crack. So think of it that way. Another thing that I always point out too is in the mining industry, if any of you are familiar with mining, they're called bacon strips when they go to when you have surface areas inside the mine. Mostly, typically, it's going to be the walls, but predominantly up in the ceiling and the headspace. They take the metal what they call bacon strips, or metal strips that are put up, and they're literally drilled, bolted in, and then they fasten them in with typically epoxy, hydraulic type of cement to kind of hold. That helps hold those cracks together so that large areas of the rock is not falling down on the mining operation or blocking up. So a little bit of extra information for you guys. Now, steel and reef reinforcement can also be used to repair structural cracks, and that would be by embedding steel reinforcement bars across the crack. That's called doweling, and this method, channels are drilled roughly perpendicular to the crack from one side of the crack section to the other, and then the steel bars are epoxied in place so as to bridge the crack. The number and location of the steel reinforcements are as necessary to restore tensile integrity across the crack. And this method may be used in combination with sealing to provide additional reinforcement. Another method of reinforcement used to repair longitudinal cracks in roadways and airport runways is cross-stitching method. Now, this is a method where holes are drilled at approximately 35-degree angles through the crack, with the next hole being drilled through the crack at the same angle from the opposite direction, and then steel bars are embedded into the holes with epoxy. This causes a crisscross stitching, and you want to repeat that as necessary to adequately strengthen the crack. Bandaging. When a crack will remain active and movement can be tolerated, this is when you can have some movement, a surface seal or a bandage may be used, which would be a flexible strip that's placed over the crack with only the edges of the strip attached to the concrete. In areas with traffic, coating and wearing coarse or aggregate broadcast is commonly used to protect the bandage. So you're going to go over and you're going to dress over top of that. Coating can be done that way. And this technique will especially be useful if movement will occur in more than one plane. Let's do this. We talked a little bit about post-tensioning, and then I'm going to go. Let's go to routing and sealing. This is the most common method used for repairing non-structural cracks, is routing and sealing. In this method, a groove is routed the length of the crack and is filled with a suitable sealant. The sealing material used depends upon the expectations of the seal, and epoxy compounds may be used if the crack is not dynamic. If the crack is active, elastomeric sealants such as polysulfide, polyurethane sealants should be used. In a flexible sealant repair, it's advisable to place a bond breaker or a backer rod at the bottom of the routed groove, to ensure that the sealant adheres only to the sides. Now, if the sealant is not restrained along the bottom of the groove, it's better able to accommodate movement without failing. If elastomeric sealants are used, hard-willed traffic may cause a crushing of the edges of the sealed crack repair. Another method, and I think this one we're going to go and finish on this one, and I want to go into the coatings part. Injection and vacuum sealant application. Now, we were talking about a lot about with epoxies, and epoxies in this situation can be injected into structural cracks, and then epoxies and other polymers can be injected into concrete cracks to seal them where there's no structural repair is necessary. One component urethane sealants can be injected into cracks to form a leak-proof seal in hydraulic structures or in below-grade applications. The urethane reacts with water to form expansive foam that seals the crack. You can use grouts that will react with water, forming a solid surface area, and also used to seal cracks in moist environments. Unlike epoxy, these systems can be used in cracks that experience a small degree of movement. And let's go ahead and we're going to go into concrete, the repaired coating repaired concrete. And a lot of this information actually is coming from I had taken concrete coatings inspector. I have level 1, which I would say at best it would be like a technician. So think of an inspection technician. The other thing is concrete coatings basic and other concrete courses that I've taken with through ACI, and then some of the work that I have done with ICRI, which would be the Concrete Repair Institute. So let's go ahead and talk a little bit about coating repaired concrete. And when we really think about concrete, when you have repairs done, surface preparation is super critical. And concrete is a different animal than steel. And I actually think with concrete, it's a little bit, it can be a little bit more challenging to prepare. And I think as the contractors that do the work, that do a lot of concrete work, and those craft workers that do the work, those inspectors that inspect it, they gain that experience, and I really appreciate that, because I remember some of the stuff I've done with concrete, and it is definitely a different animal. But when you're looking at concrete a concrete as a substrate, it has really low cohesive strength compared to pretty much any other substrate, and so surface preparation is super critical for the coating adhesion. Now, the outermost concrete layer is often very much weaker than the inner concrete, and that's really due to latents, or in some cases it could be over troweling form release agents that get into the concrete, and that really kind of interferes with the bonding of the coating. Now, if curing compounds were used on the concrete, removal or verification of compatibility with the coating is required. And so, a questionable surface should be abraded off. And a lot of it comes down to how much do you need to abrade off. Now, if you're looking at different structures, if you have a wastewater containment, you're dealing with a pretty corrosive, a very aggressive environment where you're dealing with hydrogen sulfide. You're dealing with a lot of, very nasty microbial type of things that could be done with concrete. We have colonies that sometimes will form almost in collaboration with the coating system. It's pretty amazing when we look at some of the environments that concrete are used. But then also too, you might have secondary containment. Maybe you have some type of chemical, and you have secondary containment. If your storage vessel were to fail, that containment is critical for you, because that's what protects, in most cases, the environment. It could protect people. It could protect your company, because you don't want to have chemical spills and things like that. So, really understanding, where the concrete is, what's it look like, the condition of it. So, some of the things you want to look at is that, and this would refer back to some of the ICRI information, is that you can have interconnected microcracking that's in concrete, and typically this is called what they call bruising. Now, this occurs when the concrete surface preparation is using impact methods. Okay, so that would be the scabblers and the scarifiers. Now, unless corrected through abrasive methods such as blasting with abrasive materials or high pressure water, that is what will really remove the softer and the damaged concrete. And then the micro cracks will provide really kind of a starting point for that to really look at that deterioration of the concrete. Now, some of the factors that affect coating selection, we were talking about earlier, talking about with the cargo, the commodity that's in, let's say if you're dealing with containment, or wastewater where you're dealing with wastewater treatment. So we talk about chemical exposure. Now, frequency of chemical and environmental exposure dictates the chemistry and the thickness of the coating. Since concrete is an alkaline substrate, coatings for concrete, particularly fresh concrete, must be alkaline resistant. And a coating that is not alkaline resistant will eventually deteriorate unless an alkaline resistant undercoat or primer is used. Now, mild chemical exposures such as de-icing salts may require a barrier with modest chemical resistance, such as when you're looking at let's say you're looking at some of the coal tars and methyl and some of the other type of coating systems. But harsher environments may require more chemical resistant multiple component systems such as epoxy, polyurethane, polyester, or other coating systems. Now, generally, the harsher chemical conditions also necessitate a thicker barrier, and mild exposure barriers are typically less than 40 mils, where severe exposures can require very thick barriers, let's say in excess of 250 mils thick. Hydrostatic pressure resistance. Now, when you're dealing with below grade treatments, they have to be able to withstand hydrostatic pressure, there are many coating systems that are used in positive side hydrostatic pressure applications, and these form a kind of a barrier system. They can be liquid applied, they can be sheet applied barriers, preformed barrier systems that can be done, and also cementitious membranes. Now, a coating may be required to withstand negative side hydrostatic. Oh, let's bring Bruno. Bruno, what's up, buddy? I'm sorry I missed you there. All right, Bruno, you can unmute yourself, my friend.
Oh, I'm sorry. I just want to say I love you, brother. I came here just to listen to you, man.
Oh, you're the best, man. I appreciate it.
And you're the best.
All right, I'm gonna throw you back in the audience, buddy.
All right.
Well, there we go. Thank you, Bruno. So we were talking about with coating to where you might need to have it withstand a negative side hydrostatic pressure. In this case, the bond strength must be greater than the hydrostatic pressure. Cementitious metallic oxide and other types of capillary waterproofing materials are typically used on negative side hydrostatic pressure applications. Now, let's talk about curing compounds. The ability of water and water vapor to move through a coating influence the coating's choice. Curing compounds are applied to fresh concrete in order to prevent the loss of water during the early hardening period, and the use of curing compounds increases the hardness and abrasion resistance while diminishing the chance of cracking, scaling, and dusting. However, if the curing compound is not compatible with the coating systems, they can cause delamination and must be removed prior to coating. And then breathability. Some systems may require the coating to be able to breathe, and that's really to allow water vapor to pass through. Cementitious and latex coatings are often used in applications like this that require, higher water vapor permeance, such as above grade exterior applications, and requirements for resistance to the transmission of water. And water vapor must be clear before an appropriate coating system can be identified. Now, if you don't really identify this properly, you can have a situation where the water that's trapped in the concrete can cause that freestall damage that earlier in the opening of the live chat I talked about, which would damage concrete and cause coating failure. So the things that we want to kind of leave this with, whether a substrate has dormant or active cracks, it affects what coating systems would be appropriate. If the concrete has dormant cracks, then more rigid systems such as cementitious coatings, non-elastomeric latex coatings, or solvent-based sealers can be used. When applying a coating over concrete with repaired active cracks, an elastomeric coating should be used. Otherwise, the coating will fail over the crack, and elastomeric coatings will stretch and accommodate limited substrate movement. The polymer chemistry of the elastomeric coating depends on the coating purpose and expectations. For example, an elastomeric neoprene or neoprene bitmus blend waterproofing barrier will resist the hydrostatic pressure for a below grade application, but lacks the requisite weather resistance to be used exterior above grade. Acrylic or silicone elastomeric emulsion coatings have good resistance to ultraviolet light, would be more appropriate for above grade exterior applications, and more wear resistant systems such as elastomeric polyurethanes would likely be appropriate for traffic areas. I think that's pretty much what I wanted to cover this evening. If anybody has any questions or would like to contribute to the live chat, just raise your hand and I will bring you up on the stage. If not, I appreciate everybody who attended this evening. And I will, here we go, Rudy. Let's bring you up, Rudy. Allow to speak. There you are, Rudy. Just unmute yourself, buddy.
Hey, hey, Jim. How
Yeah,
you doing?
doing great,
Great
man. I appreciate you
presentation.
being here tonight. Thank you, sir.
Hey, so I just wanted to comment kind of back
Oh, you're cutting out a little bit, Rudy. Can you hear me,
the
Rudy?
condos. Can you hear me?
Yeah, you
I
kind
can
of
hear you.
faded.
Can
Oh,
you hear me?
you disappeared a little earlier there. Can you start over?
Okay, sure. So I wanted to just comment on the discussion with the concrete structure.
Yeah, you faded
And
out again, buddy.
I want to torture everybody.
Hey, Rudy, you there?
I'm here. Can you hear me?
Yeah, when you talk, it seems to like you're out of cell reach error.
Yeah, I am on my cell phone. I don't want to torture everybody with poor sound quality here.
Yeah, we can hear when when you're not making a point. We don't hear you. But when I'm sorry, when you're not making a point, we hear you. When you're making your point, we can't hear you.
Does this sound any better right now? And I'll try
Right?
one more
Yes.
time.
Go for it.
Okay. Okay. So basically, what I wanted to comment on was the subject of rebar. And with regards to bridges and other structures, I think an interesting mechanism of failure is that the steel, when it begins to rust, it scales. And when it expands, that expansion causes the concrete to start to fracture. So not only is the reinforcement of the steel failing, but the dimension of the steel causes the surrounding concrete to rupture. So, and you'll notice that a lot in bridges that get salted or any structures near high salt content weather. That is all.
Very,
Great job. Thanks.
yeah, very good point, Rudy. Very good point. Yeah, and that's the insidious part of it is that the concrete might it's going to be giving you signals that there's something going on, and if people don't catch them right or understand them, it's a matter of time. So when we have a lot of these collapses and it happens, and then corrosion is the big issue, and you're like, my goodness, in Pittsburgh, we have some bridges that are concrete. They're having some issues for years now, and some of them are being addressed. But we use road salts and de-icing agents and things, and it's what it does to concrete is just incredible. All right, Rudy, thank you so much. Oh, well, everybody, I really appreciate it. So next Wednesday, I will be up in the great country of Canada, and I will be doing some business up there. So unfortunately, I'm not going to be able to do a Wednesday live chat, but hopefully I should be able to be back the following week. And then we've got the AMP conference coming up. If anybody's going to AMP conference, I'm going to be there and looking forward to shake your hand and have some good times in Denver coming up at the near the middle. I guess it would be what, the 18th or 19th of March. So, all right, everybody, I will put this on audio. I will edit it and I will get it up, put it on my YouTube channel, and then promote it out on LinkedIn as well. So if you guys want to share it with anybody, appreciate it. Thank you, everybody. Have a good night, good morning, or good afternoon, no matter where you're at. Thank you, guys.